Roll. Let's get started. Uh, Given the pip install sklearn gives me an error in Spider. Interesting. Okay, so let me confirm for you that scikit-learn that I gave you the right pip install, because I might not have given you the correct pip install. I did not give you the correct pip install. The pip install I gave you was incorrect. You want to use pip install scikit-learn. My apologies. Scikit-learn. So scikit-learn is not working. You want to use pip install scikit-learn. All right. So I had a couple more demos planned, but of course, timing is great, as in I'm not good at it. So we're going to skip ahead to a clustering demo. So far we've been doing machine learning. We've built a logistic regression model. And that's one type of machine learning model that we can build. And it's what we would consider a supervised machine learning model. Now, what happens if we have data that doesn't have any known labels? So far we built an algorithm to make predictions based on known labeled data. Now, what happens when we have data that does not have labels and we want to search for relationships or patterns in that data? What can we do? So this is where unsupervised machine learning can help us out. So we're going to construct a model. We're going to construct a model here. And this model, we're going to be using some unsupervised, we're going to be using some unlabeled data. This data file has attributes of 140 people. Their record contains their age, gender, blood pressure, diabetes status, weight, height, smoker, fever, and whether they have a cough. We have been asked to determine if there are any trends in the data. The data file that we're going to look at is demo2 unlabeled.csv. Again, this is available on the GitHub. This is a fictional data file generated by ChatGPT. Our great friend ChatGPT rears his head once again. And this contains a record per person with their health information. Let's take a quick look at that file in Excel, shall we? So this is demo2 unlabeled.csv. Let's take a look at it. So this time we have age, gender, blood pressure, diabetes, weight, height, smoker, fever, cough. So now this is, and I believe this is a completely different, yeah, this is a completely different data file from our original data file. So brand new data file. And we have no outcome labels. So we just have a bunch of data. This is just a stack of data about people. And we are tasked to find out, what are the trends in this data, if anything? So what we may want to do is, in the morning session, we saw that we could do k-means clustering. So we could divide this data into a couple of different clusters and then analyze the clusters and say, okay, well, try to computer figure out how to group this data, find the best way to group this data. And then once we've got those groups, say, what are the trends inside of those groups, if any exist? So let's first try to cluster our data, and then we'll do some analysis on trends. So let's flip back over to Spider. And I am going to need to bring in pandas as PD. And first thing I'll do is I'll save this file. So this will be live demo2.py if you're following along later. And I'm going to, in my data, in my Python editor, I'm going to click this double trash can here to remove all my variables, clean up my variable explorer, and then I'm going to right click and clear console in my console area. So I've got a nice clean environment to work with. So first thing we're going to do is read in our data. So data equals PD read CSV, 140 rows, 9 records. So same thing we were just looking at in Excel. Now, before we can make clusters, we need to be dealing with all numeric data. And in fact, before we make clusters and before we start analyzing those clusters, we need to have all numeric data to work with. So we're going to need to transform gender, blood pressure, diabetes, smoker, fever, and cough into numbers. We're going to need to encode these text values into numbers somehow. And how we're going to do that is by using a process that is, or a technique that is known as one-hot encoding. What does one-hot encoding mean? Encoding means that we're going to create a category, we're going to create a new column, and we're going to say it will have the values 1 if a condition is true, and it'll have the value 0 if a condition is false. So for example, we can use the attribute gender. We created a one-hot encoding for this to say if the person is male, we use the value 1, and if the person is not male, we use the value 0. We can also do this with the different forms of diabetes. We could say, is type 1 diabetes? Is type 2 diabetes? We could do the same thing with fever, with smoker, with cough. We could do the same thing with blood pressure. Is it elevated or is it hypertension? And before we get too far into this, let's explore our data just a little bit so we know what we're dealing with here. So if I take a look at our, for example, so I've got the columns age, gender, blood pressure, diabetes, weight. What values do we have for blood pressure, for instance? How many categories am I going to need to encode? I could do print data blood pressure. So I'm going to print out the blood pressure column dot unique. And so I'm doing just some basic data exploration here, and I see I have 4 values: normal, elevated, hypertension, and hypotension. So let's say my first task is I want to encode the blood pressure column and turn this into a 1 or 0 variable. Well, what do I want? What's the important information that I want to capture? Well, in my case, if somebody is high blood pressure, I want to know about that. And let's define high blood pressure as they have elevated blood pressure or hypertension. Does that seem reasonable? Any objections to that strategy? That we consider somebody with high blood pressure to be in an elevated or hypertension state? So how do we do that? Well, first off, I'm going to make a second data frame called data subs. I'm going to call this data subset. So this is what we're going to be building the clusters on. And data subset is going to be equal to data. And I'm going to grab the age, weight, and height columns. And then onto this data subset data frame, I'm going to start gluing on more columns. So I'm going to create a new column called data subset, and I'm going to call this column has high BP for has high blood pressure. And I will set this equal to, well, first off, I'll set this equal to what we're going to call a filter condition. This is something that I go into more detail in the DABI2 course, where we're filtering large data sets. So I'm going to create a filter condition that says, give me the data. I'm going to check for rows where the person's blood pressure is equal to elevated. Now, if I look at data subset, I have a new column here that says has high blood pressure. And it says false for a lot of the rows. In fact, it says false for all of the rows. Why is that? Well, that is because we're looking for an exact match, and I put in a capital E for elevated. If I run this again, you'll notice that I now have some rows that return true for has high blood pressure. Now, if I compare this to the original data frame, though, we see that row at index 6 has hypertension. But this person hasn't been classified as has high blood pressure. So I need to expand on my filter condition. I need to say either the person's blood pressure is elevated or the person's blood pressure is hypertension. So what I've said here is generate a new column that has the value true, 1, if the person has elevated or hypertension for blood pressure. 0, false, or 0, otherwise. This is a one-hot encoding of our blood pressure column. So now if I look at data subset and I compare it to my original data set, anywhere where we've got elevated or hypertension, that is now being encoded as has high blood pressure. And then I could do the same thing for, let's say, type 1 diabetes. So data subset, type 1 diabetes, I could say that is equal to data diabetes equals type 1. And I could do the same thing for type 2. So I'm doing one hot encoding for type 1 and type 2 diabetes since they're two different diseases. So I've now got one hot encoding for type 1 diabetes, type 2 diabetes. I could do the same thing for fever. So give me data subset where the original data set has a value of Y for yes. So now in my subset, I've done the one hot encoding for the fever column. And then I could do the same thing for cough. And finally, the same thing for smoker. Now, you might be wondering, Elias, I see that you've got numbers for the age, weight, and height columns, but in all these new columns that you just created, you've got true and false. What's going on here? Well, in the background, true and false are just encoded by the values 0 and 1. 0 for false and 1 for true. So we here are going to be able to use these in our clustering algorithm, no problem. Now, you might also be wondering why we had to do this in the first place. And that is because our clustering algorithm doesn't know what to do with these text values. So we need to have numeric or numeric capable data. For example, these true and false columns in order to be able to do our clustering. Now, before we create our clusters, we're going to do something called scaling our data. So we're going to use scikit-learn. We're going to use scikit-learn again. And we're going to pre-process our data. So this is, right now we're in the data preparation phase. We've done a little bit of data cleaning here where we've re-encoded our data from text values to true and false. Whoops. Now we are going to prepare our data so that we can build clusters. And what we're going to do is we're going to do something called scaling our data. And why do we need to scale our data? What do we mean by that? Well, these columns, so the age, weight, and height columns have different scales. And these could end up influencing our eventual clusters by a large margin. We don't want any of these, we don't want these columns to have undue influence over the clusters that we create. So what we can do to get rid of the effect of the scale of the units is that we can standardize our unit scale across all of our variables by using the standard scaler and then build our clusters based off of that. What the standard scaler does is for each column, subtracts the mean to center our data, and then divides the data by the standard deviation so that we have a mean of 0 and a standard deviation of 1. It does that for all of our columns. So here's how we do that. We bring in scikit-learn.preprocessing import standard scaler, and I'll add these comments in as well. I'm going to create a new variable called scaler. Scaler equals standard scaler. And our data scale data frame is going to be equal to scalar.fit_transform data subset. So let's take a look at data subset, and let's take a look at data scaled. These look completely different. But the key takeaway here is all of the columns now are on the same scale. So the impact of age, weight, and height will not unnecessarily skew our clusters one way or the other. And now we are ready to create our clusters. Now, how are we going to create our clusters? Well, we're going to bring in another function from scikit-learn, and that is called k-means. So we're going to do k-means clustering on this standard scaled data. So I'll come back at the top, say from scikit-learn.cluster, import k-means. Head to the bottom here. And I'm going to create a k-means cluster. I'm going to say k-means equals k-means. And my number of clusters, I'm going to create, let's create 2 clusters. Now, I'm also going to set the random state. So I can say random state. Remember earlier the way that the testing and training data got split up, we could control that random state. I'm going to control that random state again, just for purposes of this example. 809, 805. That's the random state I'm going to use. I just pulled it out of thin air. So we're going to create 2 clusters. Our random state is 809, 805. Now let's fit this model. So we're going to do k-means.fit, and I'm going to pass in my data scaled. And we have our clusters, but our data has not been modified. So how do we determine which cluster each piece of data, each row of data belongs to? Well, we can get that data. We can get that easily enough. We could say our original data cluster. I can create a new column called cluster on my original data, and I'll set that equal to k-means.labels_. And if I take a look at my data frame now, I've got my cluster number. I could also put this on my data subset data frame. Data subset cluster equals k-means.labels. So I can now see which cluster each row of data belongs to. And again, I've just created 2 clusters in this case. So we've done clustering. We're done, right? Not quite. Not quite done yet. What we need to do, so this is what I ran into when I was first working with clustering, is you're filled with lots of I found that I was filled with lots of excitement. It was really cool to build some clusters. It was great to do some machine learning. But then I was like, okay, well, now what? We've got 2 clusters. Our data is in 2 clusters. Now what do we do? I still need to find trends in these clusters. So we can cluster our data. Now what? Let's answer the now what. We can use the MLExtend library, the machine learning extension library in Python, and figure out what attributes appear together in a given cluster. So now we're going to do some data exploration. So for example, a question that we could ask is, do diabetes and high blood pressure exist together? If we see the presence of diabetes in a cluster, what else should we expect to see? Now, when we're taking a look at, when we're doing this kind of analysis, it's similar to asking the question that I brought up at the beginning of this workshop, which is, say you're working on an app like Instacart, where you're doing grocery ordering, and you see in the person's cart that they've ordered eggs. Well, what else, if we take a look at all the people that, everybody's grocery orders, what do they seem to order together. And we see that the pattern is, well, most people seem to, if we make our clusters, we see that most people seem to order eggs with milk. And so that's how we get the recommendation. So this is how we go one step beyond just, say, clustering the data. This is where we start to get into some data exploration using machine learning. Now, keep in mind, we're not making, so right now, we haven't really made any predictions. We haven't said label or don't label this data. All we've done is say split this data up into groups that you feel is appropriate based on all of the attributes of that data. That's all we've done. What these clusters mean to you will depend on the context of what you're researching. So all we know is that this data is that the machine believes that anything in cluster 0 seems to belong together and anything in cluster 1 seems to belong together. That's all we know right now. That's all we know right now. That's what we can conclude. What that means for you will depend on your research objectives. All right. So what we're going to do next is we're going to see what attributes seem to occur together. And we can use the MLExtend library to explore this. And we're going to use two functions from that library. And the two functions are a priori and association rules. What a priori does is it tells us what are the frequent items in our one hot data. So this is why we needed to also re-encode our data to be one hot data, like high blood pressure, T1D, T2D, is in order to find the associations, we need this to be in the one hot format. So here's what we're going to do. We're going to explore these clusters by doing the following. I'm going to create a list of clusters. So I'm going to say cluster list equals, and I'm going to create a list of my two clusters. And I'm going to say cluster 0 equals data subset. And I'm going to filter data subset where data subset cluster equals 0 and cluster 1 equals data subset where the cluster is equal to 1. I'll put these two into a list, cluster 0, cluster 1. Then what I can do, actually, do I want to do it that way? Yeah, let's do it that way for now. So what I'm going to do is I'm going to say for cluster in cluster list, I'm creating a loop. I'm looping over all of the items in this list. I'm also going to declare one more variable called cluster number, and I'll set this equal to 0 for now. This will come in handy in a moment. I'm going to print out to the console an alert for myself to say analyzing cluster number. Then I'm going to create a new variable called frequent items equals a priori. And then in brackets, I'm going to pass in cluster, and then in square brackets, another set of square brackets, the columns that I want to see what items appear together in this cluster. So for example, T1D, T2D, smoker, what else is there? Fever, cough, and has high BP. Then I have to say, okay, what's my support level? I want to say, what's the threshold of these items occurring together? I want to see them occurring together, say min support. I want to see them, I want to see items occurring together at least 50% of the time. And then use call names equals true, because we want to preserve column names in our output. Otherwise, we just get numbers and nothing makes sense. And then I'm going to print out frequent items. And I'll implement cluster number equals cluster number plus 1. so that I print out the right message. So what's going on here? So what we're going to do is we're going to grab for each item, for each of the clusters in our list here, we're going to grab the cluster and then we're going to say, give me the items that appear together at least 50% of the time in this data set. And look at the following attributes: type 1 diabetes, type 2 diabetes, smoker, fever, cough, lung cancer. Then we're going to print out that frequently occurring list to the console down here. And if we run this code, we see that in cluster 0, nothing meets that threshold. In cluster 1, we see the following. We see 75% of the time, it looks like type 2 diabetes, has high blood pressure, and smoker occur together. 54% of the time, we see has high blood pressure and cough appear together. 84% of the time, we see smoker and has high blood pressure appear together. 88% of the time, type 2 diabetes and has high blood pressure occur together. And that's the occurrence of those items in this cluster. For example, 90% of the items in cluster 1 have type 2 diabetes. So if I open up my data frame explorer, sort this data by cluster, and take a look at type 2 diabetes, just eyeballing it, a lot of these entries have type 2 diabetes equals true. A lot of these entries have smoker equals true. So these are the trends that we're seeing. We're seeing in 90% of cases, in 90% of the rows in cluster 1, type 2 diabetes occurs together. In 86% of the rows, smoker appears. 55% of the rows, cough appears. 75% of the rows, type 2 diabetes, has high blood pressure, and smoker occur together. So we're spotting, so we can use clustering, and then, so we can use clustering to divide up our data, and then we can analyze the cluster to say what attributes seem to occur together often. So how could we then use this data? Well, maybe we could use, let me ask you, so we've got these clusters, we see these trends. What does this say to you? What is this data kind of saying to you? If we take a look at, cluster 0, nothing really going on. Cluster 1, we see type 2 diabetes, smoking, has high blood pressure, seems to occur a lot. What does that say to you? How could we interpret the cluster number? And feel free to type it in the chat if you'd like to. So one interpretation could be healthy and, maybe not so healthy, for sure. We could say that this is, maybe high risk individuals versus low risk individuals. If this was, I know that in one of my previous gigs, I did some work with an insurance company, and they had models to figure out health insurance premiums for personal insurance and for life insurance. And they'd use tables like this as well, where they'd say, okay, let's take a look at, the trends. Let's take a look at trends of where we, what costs us the most. And, we'll do something like this. We'll cluster the data and then do our pattern analysis and say, oh, okay, well, we see type 2 diabetes, has high blood pressure, and smoker occur together. So that seems to be where we pay out the large claims. So again, this unsupervised machine learning allows us to take data that we don't have any labels for, just, structure. We're still working with structured data, but it allows us to take a look at this data and say, okay, what are some trends going on? And notice that we did not have to say, give me the, let's compute a score for, if this person has type 1 diabetes and type 2 diabetes and is a smoker and has a fever and has cough and has high blood pressure, then you put them in this cluster. Otherwise, you put them in that cluster. The computer did all this for us. It just crunched away at the data and tried to find some trends on its own. So we didn't have to hard code any of the rules. The computer came up with the rules came up with the classification rules based on the data that it was fed. Now, one other exploration that we could do is we could say, we could also print out the association rules. You may have noticed that I brought in a second function here called association rules. So what the association rule says is, given X occurs, what's the likelihood of a bunch of Y's occurring after it? So for example, given that type 2 diabetes occurs, what should we expect to see occurring along with type 2 diabetes? So we see that these occur together, but now we can also compute probabilities of, given type 2 diabetes, what's the likelihood that has high blood pressure and smoker occur as well? Now I need to wrap this in something called a try-catch. And what this does is, because if frequent items is empty, and in cluster 0 it is empty, this is going to throw an error. And I don't feel like handling it, so I'm going to use a try-catch to say if an error occurs, just dump out in a graceful way. So I'm going to say try rules equals association rules, and I will pass in my frequent items. I'll say metric equals lift, and min threshold equals 1. And then we'll print out our rules. And then if we have an error occur, we print no major relationships. So now if we take a look at this, what do we get for major relationships? Well, we see that high blood pressure. So let's see. So we get a data frame with 2 rows in it, which is, we see that if somebody has high blood pressure, we tend to see cough. And if somebody has a cough, we tend to see high blood pressure as well. And we seem to see that about 97% of the time. If somebody has high blood pressure, then a cough follows. So interesting way to explore these data sets further. And again, this also depends, the clusters that we get, and the clusters that we get also depends on this random state. So if I put in a random state of, say, 9, I get a completely different output. So for example, in cluster 0 this time, I have a cluster that has smokers. And in cluster 1, my rules are completely different. And I see that I have a bunch of different associations. If I just make up another random state, again, I get different clusters. My first cluster has smokers in it. So interesting. Again, I could make more clusters as well. I could say, give me 5 clusters. Now we could get into maybe some overfitting here if I have too many clusters. But yeah, cluster 0, we see type 2 diabetes, smoker, cough, blood pressure. So that looks like that might be the type 2 diabetes cluster. This cluster also has type 2 diabetes 100% of the time. Interesting. Oh, right, because I need to iterate over more than just one cluster. Anyway, so great question. How do you determine the optimal amount of clusters to use? I had code for this. I cannot find it right now, but there is a metric that you can test to say, let me look up my notes real quick here. So I want to look up my notes here. Give me 1 second so I give you the right answer. But there is a metric that you can essentially test where you optimize for, you start with, say, create 2 clusters, look at the score, then create 3 clusters, look at the score, create 4 clusters, look at the score. And there's kind of an inflection point where you start getting diminishing returns. You say, okay, our ideal number of clusters is this, like 4 or 5 clusters. And let me look up my notes real quick. So it is, I'll see if I can find it here. So yeah, if we're doing the if we get the optimal number of clusters, I have to find, I had that a while ago, and I should have had that code up. So the actual method itself is called the elbow curve method. The elbow curve method. And what we're trying to figure out is, like, as the point at which the variable that we're optimizing for, where we get to that diminishing returns. And every time you do this, what happens is you run this this algorithm, and you see a graph that just, starts plummeting a lot. And then all of a sudden you reach a point where the distance between, say, cluster 3 and cluster 4, or cluster 4 and cluster 5, is minimal. And so you go, okay, so we've hit the point where it's not worth making any further clusters. So, and the way that we do that is via something called the inertia of our cluster. So I'm actually going to do, okay. You ready for this? I'm going to do a live code demo that I have not tested yet. Okay. So hold on. This is where I love doing live demos that I've not tested. So here's what we're going to do. So I'm going to say so I'm going to say cluster test equals, I'm going to create 2, 3, 4, 5, 6, 7, 8, 9, 10. So cluster, and then I'll create a new variable called cluster inertia equals an empty array, or empty list. So for cluster size in cluster test. So what we're going to do is create I'm going to say k-means test equals k-means n clusters is equal to cluster size. And I will set the same random state for each of these. I'll say random state is 9. And then I will print out for cluster size of cluster size. Inertia is k-means test dot inertia. And I also it would also help if it fit the model. So k-means test dot fit data scaled. And then we push, and then we do cluster inertia dot append. I'm actually going to pull this out into its own variable called inertia. I cannot spell inertia correctly at all. And then the rest of the code will come back to after. Okay, so this will be live demo to be cluster ideal size. Yeah, somebody pointed out typo inertia. Thank you. I am not good at, I can't spell today. I'm sorry. Okay, and also, we're going to plot this out, because this is an example where data visualization can help us out as well. So I'm also going to bring in matplotlib.pyplot, because we're going to create a graph. And so what I'm going to do after we run all of these, after we do our fitting here, we do all these models, I'm going to plot. I'm going to do plt.plot, and then I'm going to plot out my cluster test, cluster inertia. So cluster test, the cluster number, the cluster size will be on the x-axis, and then on the y-axis will be the inertias. And again, it would help. It would really help if I could spell. So cluster inertia. Yeah. All right, so plt.show, and I'll do plt.x label is cluster size, and y label is our inertia. That choose. And okay, so this is not as well defined as I thought it was going to be. So once we get to a cluster size of about 5, we start to see diminishing returns. Well, let's go further though. Let's test cluster sizes from 2 all the way to 16. There we go. So yeah, it looks like we get diminishing returns right around 5, a cluster size of 5. So we could eyeball that and say that that is our optimal number of clusters is 5. Again, it depends on what you're doing. Now, the specific maths behind that, don't ask me. I have not researched that. Again, I'm not a trained statistician. I can just build these models. But that is your strategy for building up your, that is your strategy for building up, for trying to diagnose what is your ideal number of clusters. And so if I actually pull up the k-means documentation live, let's actually take a look here and see the attributes. So, and the attribute we're looking for is the inertia. So the inertia is the sum of squared distances of samples to their closest cluster center weighted by sample weights if provided. So there is, again, there's maths behind this to say that once we get to a certain point, we hit diminishing returns, and we shouldn't increase the cluster sizes. So I'll leave that as an exercise to you. The summary of this is that your ideal number of cluster sizes is when you reach that diminishing return. So here it looks like about 5 clusters. That would be your guideline quick method of saying we have enough clusters. Does that answer the question sufficiently? I hope so. All right. I'll assume that it does. And again, I'll post this code after the session is done. So if we say we did 5 clusters, I'm actually going to modify this code and say, you know what, we did the elbow method and we said we've got 5 clusters. That's our ideal number of clusters. I'm going to modify this code. And I'm going to say, let's see here. Again, I'm just going to pull up my sample code so I can save us a little bit of time. I'm going to actually grab my cluster list by saying, or actually the clusters that I'm going to iterate over by saying cluster list equals data subset cluster dot unique. And then I'm going to say cluster number in cluster list. And I'm going to say cluster equals data subset, because that's what we're looking at. Yes, data subset, where data subset cluster equals cluster number. And then I don't want to mess with cluster number there. There we go. Okay. So now if we take a look at the output from, and actually I want to sort these cluster numbers so that we look at the clusters in order. So I'm going to do data subset dot sort values. I'm going to sort by cluster. Do line continuation. Grab the cluster column.unique. All right, cool. So now we take a look at the clusters in order from 0 to 4. So cluster 0, 84% of the time, type 2 diabetes occurs. We see that in 57% of cases, type 2 diabetes has high blood pressure and smoker occur. Cluster 1, type 2 diabetes occurs 100% of the time in cluster number 1. Interesting. Cluster number 2, no major relationships. Cluster number 3, that's our smokers cluster. Cluster 4, that's our type 1 diabetes cluster. So that might be why we have, so interesting. So we've got one cluster that doesn't seem to have any major relationships, one cluster that seems to have relationships between, say, type 2 diabetes, blood pressure, and smoking, a cluster that has where everybody has type 2 diabetes, a cluster where everybody's a smoker, and a cluster where everybody has type 1 diabetes. So very interesting clustering of that. Very interesting output of the clustering algorithm. And so that's k-means clustering. And that's doing some data exploration using using cluster exploration. I get really excited about this stuff. I think this is so cool that we can feed computers just, a bunch of unsorted data, a bunch of, unsifted data, unlabeled data, and it can figure out some attributes about this. I mean, let your imagination run wild about what you can do with it. And you can also, I would say that you could, it's not a stretch to see why, getting back to Annado's point way at the beginning of the day, how we could get into some serious danger without any sort of guidance about how to use machine learning, because it's not a major step from this to, like, we're on the precipice right now of being able to do, say artificial intelligence, anything related to artificial intelligence. Like, these are the kinds of algorithms that start to feed into, doing AI work. It's basically this, just a little bit more, just more complicated. So, you could say, so, and this is where we get into issues of like, well, okay, so again, go back to the insurance company example. We can say, okay, well, smokers, we know, we see that our high claims seem to occur with smokers. So do we give them coverage? And so, all of a sudden we're making data. Now we can make data-driven decisions based on machine learning, based on what the algorithms are telling us. And that's awesome. It means we don't have to follow our gut instinct, but it also has implications. I'm sure you can let your imagination run wild there, right? Like, it's not a stretch to say that this could also be used for, that this could have consequences in the real world, let's say. Okay, we covered a lot of ground on this. We covered a lot of ground on this example. Are there any questions before we move on? Because I might have one more demo to wrap things up and get us out of here for the day. So I'll give folks just a moment to type in the chat if you've got questions. Again, I will post these demos into the GitHub after we're all done. Okay, I'm not seeing any questions. All right, so I have one final example. I have one final example for us to take a look at. So we took a look at supervised machine learning algorithms. In particular, we took a look at, what was the first one that we looked at? Logistic regressions, where we did, where we took a look to say, has disease, doesn't have disease. We're trying to predict that. Well, that was one type of supervised machine learning algorithm. And then we also looked at k-means clustering and then did some inspection of k-means clustering of our clusters. Now, for supervised machine learning, One type of model that we can use is the logistic regression. We have another type of model available to us. It's called decision trees. And this is what we're going to end on. I'm going to show you a second type of algorithm here where we can build up a decision tree to allow us to classify new items based on a set of labeled items. And the idea behind the decision tree is that given a labeled piece of data, we can walk through a tree to say, let's check all these attributes and say, is this a, does the person have disease or not have disease? Now, I've been dealing with some pretty heavy stuff, health data, diseases. Let's talk about cats. So we've got a data set here that, and again, this is posted to the website. I'll pull up my demo here. We have a data set that, again, is randomly generated. It is demo3 cat species. And this demo file has a series of, cats. Let's be honest. We're on the internet. Let's talk about cats. In the different cat genuses, the subfamily, and the family. All the family is Felidae. That's the family that all kind of cat types belong to. We have, and these are all individual instances of cats. So we have their species, if they can roar, if they can purr, if they can meow, their weight, and their size. A 420-pound cat. No thanks. And we also have house cats. For example, the Felis, domestic cats. So we have a 10-pound cat that's 25 centimeters long. Cute. So what we want to do is we want to build a decision tree to say, can we identify if a cat belongs to a particular genus, given if we know they can purr, meow, roar, their weight in pounds, and their size in centimeters? Can we build a model that encodes that? And we've got 48 instances of cats. So let's do it. Let's build a decision tree that allows us to figure out if a given cat is part of a particular genus. And I've got like 8 minutes to do this. So let's rock and roll. So again, this is going to be very similar to what we did for logistic regression trees. So I'm going to bring in scikit-learn. I'm going to bring in pandas. I'm going to read CSV. I'm going to clear out my environment here. And I bring in my data. I've got 48 rows, 9 columns, weight, size, centimeters, and I have all these genuses. Okay, cool. Again, I'm going to make a subset of my data. And then I'm going to do one hot encoding of can roar, can purr, and can meow. So I've got my data subset. Weight, size, can roar, can purr, can meow. My labels are going to be my data, my genus column. So these are my data labels. And we're going to create our training data, test data, training labels, test labels, equals train, test, split. This code should look familiar. So we'll pass in data subset. Our labels is our labels. Our test size, we're going to use half the data for, we'll use half the data for testing, half the data for training. And our random state will be 23 because I felt like it. Now we create our model. And we create our model. This case, we're using a decision tree classifier. And then we got to fit the model. So we do model.fit, train data, train labels. And then we can do test prediction, test predict labels equals model.predict test data. And then we can get the accuracy by saying accuracy score. And we're going to do test labels versus test predict labels. And we'll see how our model does. And our model's accuracy is 54%. That's not a great model, if I'm honest. 54% of the time. Not bad, not great. What happens if we increase the test size to 0.8? Our model accuracy goes down, which is not great. If I put it to, say, 0.5, yeah, we go up to about 54%. We say 0.2, again, our accuracy goes down. 0.5 seems to be okay for a model. Now, here's what's cool. Here's what's really cool about decision trees. Decision trees are easy to visualize, and I'll show you. Watch this. So I also brought in plot tree from scikit-learn.tree. I can do the following. I'm going to create a new figure using matplotlib. So I'm going to do plot.figure, and I'm going to say fig size equals 48 inches by 24 inches, because these things get huge. These decision trees get huge. And I'm going to do plot underscore tree. I'm going to pass in my model, and I'm going to say filled equals true. So this is just some styling stuff. So feature names equals my data subset dot column names. And then my class names is my labels. And actually, yeah, I do labels.unique. I do plt.show, and that should give us our decision tree in the plots tab. Now that looks very small right now, but like any good cooking show, I prepared this example ahead of time. So how do we interpret? So this is the decision tree that we get from scikit-learn. So how do we interpret this? This looks like a lot. You start at the very top node, top leaf, and we work our way down. First thing we do is we take a look at the size. Say we're predicting a new instance. We take a look at the size centimeters and say, is it less than or equal to 160? If it is less than or equal to 160, we take the left branch. If it is greater than 160, we take the right branch. And we do this all the way down. So let's take, for instance, let's see here. So we're going to take the, we'll take the first row. So first row belongs to genus Panthera. It's an African lion. So can roar equals true, can purr equals false, can meow equals true, weight is equal to 420, size in centimeters is equal to 190. Okay, so this should come up with Panthera, which is interesting. I don't feel like that's accurate, but anyway, I'm not a cat expert. All right, so we take a look. So if we're doing our prediction, we take a look at our first instance here. So we say size centimeters less than or equal to 160. That is false, so we take the right-hand branch. And we then say size centimeter is less than or equal to 200. Well, our size centimeter is 190. That's true. We take the left-hand branch. We're at an end node, a terminal leaf. Our algorithm predicts that we have a leopardus, and our model got it wrong. But our model's going to get it wrong about 45% of the time, because that's the accuracy right now. So, but the cool thing is when you've got a machine learning, when you're doing decision trees like this, this is something that's fairly easy to visualize. And there are cases, and I won't get into them because we don't have time for that today. In fact, we're just about out of time, where a decision tree model could predict better than, say, a logistic regression model. And with that, we are at, it looks like 4:35. In fact, slightly after 4:35, Ethan. So I can wrap up my bit real quick, and then I can pass it back to you. How's that sound?
Sounds good, Elias.
All right. So just to wrap things up, what did we cover today? Because we went through a lot of different details. Unfortunately, we didn't get to. There was one item that we didn't get to today, which was exploring some of the Ontario COVID case data. But I'll see if I can post that online after. But just to recap what we covered today, we created a machine learning model to help create and find trends in unlabeled data, and we could create predictive models based on existing labeled data. Now, both can be used to help us find new patterns or new insights that otherwise would take us way too long to figure out on our own. It allows us to stop relying so much on gut instinct to come up with our conclusions, but we should use these to help guide our analysis and not as a substitution for our own intuition, our own logic, and our own reason. I come back to that idea of answers versus results. We have gotten results from the computer and not answers. These are not definitive, never question. This is a starting point for your analysis. This is where the real work, in my opinion, the real work begins. So with that, I'll just say real quick that, again, if this kind of content is something that appeals to you, then by all means, I would encourage you to head over to the GitHub repository where I will post the demo files and the code files. Again, on that page, there's information on how to connect with me and connect with the rest of the DABI team. Definitely also reach out to, if the coding courses if that sounds of interest to you, definitely check out the DABI program. I've left a link to my course in particular, and of course you can find out more details on the Wattspeed website. Feel free to connect with me. Happy to chat sometime. And with that, I thank you for your attention. I know it's been probably a big, heady day of machine learning, but I hope you enjoyed it. I hope you got something out of this. And I will turn it back over to Ethan to close us out for the day.